the universe from nothing, the quantum loophole that created everything. There's a moment we can't photograph, can't even imagine clearly, the instant before everything began. No galaxies, no particles, no time. Just a void with no stage, no actors, yet somehow destined to explode into existence. That's the paradox at the center of everything we know. How can something arise when there was nothing there to begin with? For most of human history, that question belonged to philosophers and theologians. It was too grand, too absolute for science. But then the math started whispering secrets. When physicists extended quantum theory to the edge of space-time, they found that nothing might not be the barren emptiness we thought. At the tiniest scales, fluctuations appear spontaneously, blips of energy, winking in and out of being. What if the whole universe is one of those blips, stretched and magnified beyond all recognition? It sounds impossible, yet pieces of evidence line up with unsettling precision. The patterns in the cosmic microwave background, the way galaxies drift apart faster and faster, the faint hum of dark energy pressing outward on the fabric of space itself. All of them trace back to an origin that should have been impossible. The universe behaves like a miracle disguised as physics. Now here's where it gets even stranger. According to quantum mechanics, the rules don't forbid something from emerging without a cause, so long as the books balance. A tiny fluctuation can appear as long as positive and negative energies cancel each other out perfectly. Matter on one side, gravity on the other. It's like the universe borrowed energy from itself and owes exactly zero debt. A cosmic loophole hidden inside the uncertainty of nature. But there's more at stake here than equations. The idea cuts deep into our sense of meaning. Physicists such as Lawrence Krauss and Stephen Hawking claim that no external creator is required, that the laws of quantum physics alone can produce a universe. Philosophers push back, saying that a vacuum filled with laws and fields isn't nothing at all. It's a very specific kind of something, dressed up as emptiness. That clash between empirical law and existential wonder didn't start in a lab. It began the moment we asked the simplest and hardest question: why is there anything here at all? And now science, armed with telescopes and particle accelerators, is circling that same mystery from a new angle. If physics can show that nothing must fluctuate, maybe the act of creation isn't an exception to the rules but a direct consequence of them. Still, the deeper we look, the less solid nothing becomes. Within the equations, emptiness seethes with invisible energy. Even the calmest vacuum hides restless ghosts of particles that flicker into being and vanish before they can exist for real. Each event is fleeting, random, yet relentless. And at that scale, before atoms, before light, before time itself, every possibility is technically allowed. In the right conditions, those quantum tremors could inflate into an entire universe. But here's the haunting part. If that's true, then the origin of everything may not carry any grand purpose at all. It might be just one quantum roll of the dice. And yet, that random act produced galaxies, stars, and us, the storytellers trying to reverse engineer our own beginning. So tonight, we're diving into that loophole, the quantum quirk that may have given birth to spacetime itself. We'll trace how Einstein's equations accidentally hinted at it, how modern physics wrestled with its consequences, and how philosophers refused to let the word nothing lose its meaning. Because somewhere between those arguments, between fields, constants, and the silence before creation, lies the strangest possibility in science: that the universe didn't start with a bang of divine intent, but with a whisper from the vacuum. And if that whisper still echoes, it means nothing never truly ended. It transformed into everything we see. The human obsession with origins. Every culture at some point has stared into the dark and asked the same impossible question: why is there something rather than nothing? You can find it carved into stone myths and whispered through creation hymns. The ancient Sumerians spoke of the god Namu, born from the primeval sea, shaping heaven and earth out of formless chaos. The Greeks imagined Gaia rising from the void. In the Rig Veda, creation was born out of a cosmic breath. Each story tried to tame the restless fear that maybe there could have been nothing at all. Because nothing doesn't just mean emptiness. It means no memory, no story, no one to tell it. Centuries later, we still circle that same question, only now our gods have equations. Yet the emotion behind it hasn't changed. When early humans looked up at the stars, they weren't doing physics. They were trying to understand why there was something to look at in the first place. The night sky was both proof and mystery, glittering evidence that the universe exists, but also a reminder that we don't know why. As civilizations advanced, creation myths became cosmologies. The Babylonians mapped the heavens to track seasons. The Egyptians built celestial order into their pyramids, and philosophers from Aristotle to Aquinas turned creation into logic. Each believed the universe had an underlying reason, a cause or a purpose that made its existence necessary. Aristotle called it the unmoved mover, the first cause that sets everything else into motion. It made sense emotionally. Nothing moves without being moved. Something must have flicked the first domino. For nearly 2 millennia, that reasoning held fast, refined by thinkers like Aquinas and echoed through theology and early science alike. But in the early 20th century, the quiet faith in a stable cosmos met its unexpected challenger, not through revelation but through mathematics. When relativity arrived, it split the sky open. Space and time themselves were about to move. The obsession with origins didn't fade, it evolved. During the Enlightenment, astronomers started to replace mythic timelines with celestial mechanics. Newton showed that gravity held the solar system together, that precise laws governed the heavens. But he left one question untouched. Where did those laws come from? He called them the workmanship of a divine power, a careful hedge between science and scripture. For a while, that balance worked. Science could describe the cosmos without explaining its birth. Then came the 20th century and the comfort evaporated. Telescopes grew stronger, mathematics reached further, and Albert Einstein rewrote how we measure time and space. Suddenly, the universe wasn't fixed or eternal. It was a fabric that could warp, stretch, and expand. The sky wasn't static at all, it was moving. That discovery blew apart the ancient idea of a timeless cosmos. If space was expanding, logic demanded that once upon a time it had been smaller, far smaller. Maybe infinitesimally small. The question of origins turned into a question of physics. By the mid-20th century, the idea of a Big Bang had taken hold, a moment when the universe burst outward from an infinitely dense singularity. Scientists didn't yet know what triggered it or what existed before. Some said nothing did. Others said time itself began there. But one thing was clear: creation had transitioned from a divine act to a physical event. And that shift didn't make the mystery smaller, it made it stranger. Because even as cosmology advanced, the emotional pull of the question never loosened. People wanted to know not just how it happened, but why it happened at all. When scientists said the universe came from a fluctuation, the public heard a different kind of miracle, one disguised in scientific language. Was that fluctuation inevitable, random, meaningless? Those questions sit beyond the reach of telescopes, but they still keep people awake at night. Psychologists would later argue that this obsession is built into us. Human minds hate uncaused events. We see patterns where there are none, invent motives for every noise in the dark. It's a survival trait that became philosophy. We crave answers that connect dots from beginning to end. A universe from nothing destroys that instinct. It's a story with no storyteller. And that contradiction gnaws at us. How can there be consequence without cause, meaning without a source? Still, each leap in understanding made the original question more compelling. The 192s saw Edwin Hubble prove that distant galaxies were receding. The farther they were, the faster they moved. The universe was expanding, and by running time backward, scientists could trace everything back to a single origin point. It wasn't myth anymore. It was measurement. But even as the math got sharper, so did the doubts. If the laws of physics describe everything inside the universe, what describes the moment those laws themselves began? Did the laws exist before matter? If so, in what sense? And under what clock? Throughout history, the search for origins mirrored our deeper insecurities. Every theory of beginning was also a mirror for human fear. Fear of impermanence, fear of randomness, fear that our story might not matter. Maybe that's why this topic endures across cultures. It isn't just about physics or philosophy, it's about identity. If everything came from nothing, then we are fragments of an accident. If not, then we're part of an intention grander than ourselves. Either answer is unsettling. In modern classrooms and observatories, we rarely mention the emotional side, but it lingers quietly behind every diagram of the early cosmos. You can feel it when scientists describe background radiation as the afterglow of creation. Even in the cold language of data, words like birth, origin, and horizon betray our awe. We don't just want to solve equations, we want to understand our own meaning within them. And so, the story of something from nothing has never been just about physics. It's about imagination. Humanity's oldest instinct is to look backward from the present and ask, what came before? That's why this question endures even when it seems unsolvable. It binds mythmakers, poets, and astrophysicists together. Every generation tries again, drawing the line of causality further back, daring to ask what lies beyond the first instant. But we've reached a strange point in that journey. The closer science gets to the first moment, the more elusive the answer becomes. Time dissolves into probability, matter into fields. The difference between something and nothing starts to blur until the words lose meaning. And yet in that blur we keep searching, because curiosity and fear are two sides of the same spark, the spark that might have ignited the universe itself. To understand how we reached this point, how the question shifted from myth to mathematics, we need to look back once more, to the moment when even the idea of a static universe was challenged by one man's reluctant equation, a symbol he introduced, regretted, and that would later turn out to hold the secret code of cosmic expansion. Einstein's reluctant constant. When Albert Einstein published his general theory of relativity in 1915, he thought he'd found the ultimate description of gravity. Space and time weren't passive backdrops anymore. They were flexible, dynamic, bent by mass and energy. But soon after presenting his theory, Einstein faced a problem he didn't expect. His equations implied that the universe couldn't stand still. The cosmic fabric would either stretch outward or collapse inward. That wasn't what anyone, including Einstein, wanted to hear. At the time, astronomers and physicists assumed the universe was static and eternal. The stars, they thought, had always been there. The idea of cosmic change seemed absurd. So Einstein did something daring for a man known for intellectual purity. He modified his own theory. He added an extra term, a mathematical cushion, to counterbalance gravity's pull. He called it the cosmological constant, represented by the Greek letter lambda. In essence, lambda acted as a kind of anti-gravity. It pushed outward just enough to hold the universe steady against the inward tug of mass. With that addition, Einstein's equations described the tranquil, eternal cosmos everyone expected. He was satisfied, at least for a while. He even called it the most natural form of the equations. But nature had surprises waiting. About a decade later, Edwin Hubble used Mount Wilson Observatory's new telescope to measure the light from distant galaxies. He noticed that their light was stretched toward the red end of the spectrum, a sign they were moving away from us. The farther a galaxy was, the faster it receded. The universe was expanding. Suddenly, Einstein's static model looked obsolete. According to later recollections, he reportedly muttered that introducing the cosmological constant had been his biggest blunder. He removed it from his equations and moved on. For decades afterward, physicists agreed that lambda was unnecessary. They treated it as a mathematical relic, a patch on reality that didn't need patching. The Big Bang theory gained momentum, describing a universe evolving dynamically from a hot, dense beginning. That seemed to close the book on Einstein's constant, but the universe wasn't finished with it. In the late 199s, teams studying distant Type Ia supernovae, the universe's exploding stars, made a jolting discovery. Those supernovae were dimmer than expected, meaning they were farther away than they should be if cosmic expansion were slowing down. The universe wasn't just expanding, it was accelerating. Something invisible was pushing it apart faster and faster. When scientists fed that data into Einstein's equations, the only way to make the math work was to bring back the cosmological constant. Just like that, the blunder became indispensable. That outward pressure became known as dark energy. Today, it's thought to make up roughly 70% of the total energy in the cosmos. It doesn't clump or radiate, and it doesn't interact with light. It simply exists as the energy of space itself, driving everything apart. And our best measurements match what a constant lambda would do: produce a steady, small acceleration that grows more obvious over billions of years. The irony runs deep. Einstein added lambda to hold the universe in a static balance. In reality, it appears to be the engine of cosmic expansion. The same symbol he tried to remove may define the destiny of everything. If lambda remains truly constant, galaxies beyond our local neighborhood will drift forever out of reach, leaving an empty, cold sky. But if lambda changes over time, as some new theories propose, the future could be stranger still, oscillating between slow and rapid expansion, or even ending in a big rip, where space itself tears apart every atom. The cosmological constant raised another question Einstein couldn't have imagined. What exactly gives empty space its pressure? According to quantum field theory, even a perfect vacuum seethes with energy. Every field, electromagnetic, Higgs, gravitational, vibrates with virtual particles blinking in and out of existence. Add up all those contributions, and the vacuum should have enormous energy, enough to curl spacetime into a tiny ball. But the real universe expands gently, not violently. The predicted energy is outrageously too high, about 10,120 times larger than what observations show. No other calculation in physics misses by that much. It's been called the worst theoretical prediction ever made. That mismatch is what physicists call the cosmological constant problem. It forces them to ask whether there's some hidden mechanism that cancels most of that vacuum energy, leaving only the faint residue we see as dark energy today. Some suspect it's a matter of symmetry. Others think new physics, maybe quantum gravity, will reveal the fix. Whatever the cause, it suggests that our understanding of empty space is deeply incomplete. Einstein's harmless add-on turned into a gateway between gravity and quantum mechanics, the very frontier physicists still can't unify. In his time, the constant was pure mathematics. Today, it's an open invitation to reconsider what nothingness actually means. When cosmologists talk about the vacuum energy behind lambda, they're talking about the restless heart of nothing itself. Meanwhile, observations keep refining the picture. Surveys like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and satellite missions from Euclid to the upcoming Rubin Observatory continue scanning millions of galaxies. Their goal is to chart how cosmic expansion changed over billions of years. If lambda has varied even slightly, those programs could catch it. Some data already hint it might not be perfectly constant, perhaps a field that evolves slowly with time. If confirmed, that would mean dark energy isn't a true vacuum property, but a dynamic phenomenon intertwined with cosmic history. Standing on this crossroad between relativity and quantum physics, Einstein's constant feels less like a mistake and more like a clue, a faint fingerprint of deeper laws. It connects the geometry of space-time with the tremors of the quantum vacuum, linking the very large to the very small. Without realizing it, Einstein built the doorway to questions he never got to ask. There's a trace of humility in that. The man who tamed the cosmos with equations still stumbled when faced with its ultimate balance. He admitted it freely, yet his error keeps shaping the course of science. The cosmological constant reminds us that even missteps can contain deeper truths waiting to unfold. Each correction drives us closer to the boundary where simple models collapse and reality begins to whisper through the math. And so, what began as a reluctant adjustment became the backbone of modern cosmology. It tells us the vacuum between galaxies isn't truly empty. It's alive with a gentle pressure that dictates the universe's fate. But that discovery only deepens the mystery. Because if empty space can push the cosmos apart, then emptiness has energy, and energy means substance. Which leaves us with a new problem. Maybe nothing isn't nothing at all. That's where the story turns next, to the strange idea that the vacuum itself buzzes with invisible power, a restless sea that makes up most of reality. The next step is to look closer at that space between stars, that seeming void where creation never really stopped. The vacuum that isn't empty. It sounds like a strange contradiction, an empty space that's full of something. But that's what modern physics tells us about the vacuum. It isn't empty at all. What looks like nothing, even in the deepest corner of intergalactic space, is actually an ocean of activity. A region stripped of particles still contains the quantum fields that define everything, and those fields refuse to sit still. In the old Newtonian sense, a vacuum was simple. You removed all matter, all air, and you had nothing left, a pure void. But when quantum field theory came along in the 20th century, it rewrote that definition. According to this framework, every type of particle corresponds to a field spread throughout the universe. Electrons, quarks, photons. They're not just objects but excitations in their own fields. Even when those fields are in their lowest possible energy state, they fluctuate. Tiny wiggles appear and disappear too quickly to notice. The average looks calm, but underneath, there's constant motion. These restless ripples create what's called vacuum energy. It's a kind of background hum, measurable only through its effects. One famous example came from experiments like the Casimir effect, where two metal plates placed extremely close together feel an attractive force, even though no actual particles are between them. That pressure doesn't come from air or heat. It comes from the quantum vacuum itself. The space between the plates has slightly fewer modes of fluctuation than the space outside, creating an imbalance that pushes them together. It's reality revealing that nothingness has weight. Now scale that up to the entire cosmos. The vacuum energy fills every cubic meter, contributing an invisible density to space. In quantum field theory, all those fluctuating fields add up. Each vibration carries energy, and when you sum them across every possible frequency, the result is absurdly large. Depending on how you set the cutoff point, somewhere around the Planck scale, the theoretical energy density of the vacuum could be 10 to the power of 120 times greater than what we actually observe. That number isn't just wrong, it's catastrophic. If it were true, the gravitational pull from that energy would have curled the universe into a microscopic bubble long ago. Galaxies, planets, even atoms couldn't exist. Yet here we are, and the observed vacuum energy is incredibly small but non-zero, just enough to accelerate cosmic expansion. This mismatch between what quantum theory predicts and what telescopes measure is the most dramatic discrepancy in all of science. Physicists call it the cosmological constant problem, and it sits right at the boundary between quantum mechanics and general relativity. Relativity treats energy as a source of curvature for spacetime. If empty space has energy, its gravitational effect should be enormous. But for reasons we don't yet understand, most of that energy seems to cancel out. Some unknown mechanism, perhaps a symmetry we haven't discovered, reduces the vast theoretical value to the minuscule level that fuels dark energy today. When people hear the phrase vacuum energy, it might sound like speculative science fiction, but its fingerprints are everywhere. Without those fluctuating fields, atoms wouldn't behave the way they do. Even the stability of matter depends on these background jitters. Virtual particles appear for a blink of time, interact, and vanish again, never directly observed but influencing measurable quantities like energy levels and electromagnetic forces. The word virtual doesn't mean imaginary,